Welcome to Reactions of Organic Functional Groups, Part 2, Redox, A Closer Look. We had a brief introduction to redox, which is oxidation and reduction, a few weeks ago, and now we're going to dig in deeper. Let's get started. All right, so we know from our previous lessons that redox is a change in the oxidation number. Can you see that D there? Oxidation number. And oxidation number is really just a fancy way to say the charge. How many electrons have been lost or gained? So back for exam 1, we learned about the oxidation and reduction of inorganic, really compounds to form ions. And so we learned the expression, Leo says Ger. And right, so Leo was loss of electrons is oxidation. All right, so there's our Leo. And then the Ger was gain of electrons is reduction. Okay, and so if this is feeling a little sketchy, it wouldn't be a bad idea to go back and rewatch that earlier video. We're going to get a little more formal now. Remember that there's always some elements that we're going to know what charge they take, right? And these are our best friends, right? So pure elements are neutral. Fixed charge, right? We know our alkaline earth, and aluminum. Those we always know those charges. Another couple that we know, right? We always know silver is +1. We always know zinc is +2. Right? And then halogens, right? Remember X is halogens. That's the 7th group. Those are always -1 for our course because we're going to only look at halogens when they're in ionic compounds or bonded to carbon. There are exceptions here beyond Chem 300 or Chem 309, but we're not going to worry about those because we're Chem 309. Oxygen for our class will always be -2, right? And whether it's bonded to, in an ionic compound or a covalent compound, I will never be asking you questions with peroxide, the exception. And I will never ask you about hydrogen as hydride, the -1. Here is, so we'll always see it as +1. All right. So the first thing we need to do before we can go to reactions is we need to feel comfortable with compounds. Now, you guys are already really good at figuring out the oxidation state, right? Lead is a variable, right? A variable charge metal. And so we've been practicing this all along, right? If we look at this compound, right? This is a neutral compound. So we know that the cation and the anion need to add up to 0. So using our table here, right? So when we see the oxygen, we know it's O2-, and the chemical formula tells us there's 2 of those. So overall, we have a -4. So we've learned, right? So then this lead must bring in the entire positive charge so that we can equal 0. So the lead must be +4, right? So the oxides are easy, and then we had to determine the lead. Now in this next example, sodium, right? Our buddy, the alkali metal, we know sodium is +1. And once again, the oxide we know is -2. And then the chemical formula says there's 3 of them. All right? So the mystery here is the nitrogen. We don't know what the charge is. Once again, when we look, this is a compound and it's neutral. So everything needs to add to 0. So basically, we just want to set up a very simple algebraic expression, right? So the sodium is +1, and then the nitrogen is what we don't know. And then the oxide, there were 3 of those, and they were each -2. And when we're all done, this is a neutral compound, so it adds to 0. So now we would simply solve for the charge on the nitrogen. So we've got 1 and -6. So I'll just switch colors here. So we have the question mark, -5 equals 0. So the nitrogen is going to be +5. So we already know the nitrogen, or the sodium and the oxide, and now we know nitrogen is +5. There we go, running out of room. So that's not very, right? It needs to be a good superscript. That's much prettier. Okay, now let's do one more, and this one's a little trickier because this one is an ion. So when we add up the oxidation states, they're not going to add to 0, right? Now we have our -1. This is a -1 ion. All right, so what do we know? We know hydrogen is +1. Carbon, once again, is the mystery. And then our buddy oxygen is oxide. And we have 3 as well. So we'll do our algebraic expression again. So we'll keep our color coding, right? So the hydrogen was +1. And then the carbon is the question mark. And there just happens to only, in each of these examples, there's only one, right? If we had multiple, we'd have to put our coefficient. And then we have the 3 oxides, and they're each oxide's blue, -2, right? And then what makes this one a little different, right, is now, because it's a -1 charge, they add, right? All of these charges have to add to -1. So we do our algebra, and so we have the +1 and the -6. So the question mark -5 equals -1. Add 5 to both sides, and so the charge, the oxidation state of the carbon is +4, right? So I'm emphasizing the one we had to figure out, but in a question, you would want to make sure to list the oxidation state of all of the elements in the compound or ion. Alrighty, so now that we're feeling comfortable with how to look at individual compounds, let's expand and start to look at chemical reactions. Alrighty, so to help us recognize which elements are being oxidized and which elements are being reduced in a reaction, half reactions are going to be very helpful. And the key to half reactions is half reactions only look at the element that's being oxidized or reduced. So step 1 will be to assign the oxidation numbers to each atom in the reaction, just like we practiced on the previous page. Then we'll look for changes in the oxidation number and write the half reactions for those elements. All right, let's practice this together. Alrighty, so step 1, we need to write the oxidation states. So once again, our buddy oxygen, right, that's going to be oxide -2. And this one's pretty simple since it's a 1-to-1 ratio. We know the copper must be +2. Now the hydrogen, right, it's pure. Have no fear of ice-cold beer, one of our diatomic elements. Right, so this is one of the, the have no fear of ice-cold beer gang, all these diatomic elements. This is the only time we're going to worry about subscripts, because this is the pure form. Now when we look at the copper, notice that now it is a 0. And here, the hydrogen, because it's part of a compound, +1, especially because it's with the more electronegative oxygen. And then the oxygen still tried and true, -2. Alrighty, so let's write the half reaction for hydrogen, right? So hydrogen started as a 0 and it went to +1. Now because of the pure state being diatomic, we'll put a coefficient here to keep our atoms balanced. And now we're going to add the electrons to balance the charge. So a 0 and a plus. So we're going to put the electrons here, right, so that the positive 2 and the negative 2 cancel. So we have 0 on the left and 0 on the right. Now let's look at the copper. Copper is plus 2, and it goes to copper 0. So here, by looking at the charge, we know to put the electrons on the left side. So plus 2 and minus 2 cancels to neutral. 0 equals 0. Alrighty. So now oxidation and reduction always occur together because the electrons lost need to equal the electrons gained. So we can't have one process without the other. There's got to be a handoff somewhere. Okay, so which element was oxidized, right? So there's our Leo says Gr. Maybe we should have reviewed that, right? So Leo says Gr, right? Or oil rig, if you like that one better. Okay, so here's the lost electrons. So hydrogen was oxidized. Oops. There we go. Okay. And which element was reduced? Copper. Right? Copper plus 2. Notice here I'm asking you about the element. Okay? So be careful with the wording of the question. Sometimes we want to put the actual compound. Other times we'll put the element. We're going to build up. So I just want that to be on your radar. Now let's look at a reaction that's a little more complex. All right? So iron and oxide, right? So we've practiced this one quite a bit. Oxide is minus 2, and now to properly name this, we need to know the charge on the iron. So there's 3 oxides. So overall, there's a minus 6, which means there's going to need to be a plus 6. And there are 2 irons present, so this would be iron 3 plus. So iron 3 oxide reacts with carbon monoxide. So there's our buddy oxide again, minus 2. And this one's pretty straightforward, right, because it's a 1-to-1. So we know the carbon must be plus 2. All right, and then let's put in our reaction arrow here to make sure we've got our boundaries. Now the iron, right, it's in the pure state. Oops, runaway pen. Right, so iron, when it's pure, 0. And then, once again, right, using our table, always start with the elements we know for sure. We know, right, oxygen will be oxides minus 2. The chemical formula shows that we have 2 present. So overall, there's a minus 4. So that means that the carbon has to bring in a plus 4. All right, so we can see that the iron is changing oxidation state, and the carbon is changing oxidation states. Let's go ahead and write the half reaction for carbon, right? So we just write the 2 forms of the element, and then looking at the charges, we're like, okay, where do we put the electrons to balance the charge? So we're going to need to add 2 electrons on the right to balance out because we only have plus 2 on the left, right? So plus 2 equals 4 minus 2. Let's go ahead and do iron. Iron starts as a plus 3 and goes to the pure form of 0. So this time, to balance the charge, we're going to need to put 3 electrons on the left. Now, you might be a little concerned here because I mentioned that electrons lost have to equal electrons gained, and it feels like I have told you a false statement. But let's be patient. Let's finish up with A and B, and then we'll look at the whole chemical reaction. Remember, because half reactions only look at the element being oxidized or reduced. So these are the correct half reactions for the elements, but we need to integrate this information with the chemical formula. And I'll show you that very quickly. But let's wrap up which element is oxidized, right? And that means lost electrons. So here they are. Here's the lost electrons. So the carbon plus 2 gets oxidized. And who's reduced? The iron. Who gained electrons? The iron plus 3, or the iron. Okay, so now let's sort out, right? And these are the gained electrons. All right, so now let's reconcile this. What's going on here? Okay, so we look at the half reaction. So if we look at the half reaction for carbon, so that's our oxidation reaction. We see that we have, now we look at the full chemical formula or chemical reaction. From the chemical reaction, we see there's the coefficient of 3 from the reaction. All right, and then from the half reaction, we see that each carbon lost 2 electrons. All right, so this came from the half reaction, and the 3 came from the full reaction. So when we put those together, we see that we lost 6 electrons. And now, if we look at the reduction, all right, now we're going to focus on the iron. So if we look up here, here is the chemical formula that the iron is present in. So from the chemical formula, we get the 2. Chemical formula, okay? And then from our half reaction, we see there's 3 electrons, right? So, whoops, make sure you guys can see this. There's our half reaction. See, so we bring together the information from the full balanced reaction and the information from our half reaction, and we bring those together. We see that 6 electrons were lost and 6 electrons were gained. So once again, electrons lost equaled electrons gained. Alrighty, so that's pretty much everything we need to know about inorganic oxidation and reduction. So now we're going to expand our understanding of redox to organic compounds, right? And organic molecules, right, are based on carbon, right? That carbon backbone. So we're going to use a different set of rules to recognize oxidation and reduction. And since organic compounds are all about carbon, carbon will be our focus. We're going to look at the carbon to oxygen bonds and the carbon to hydrogen bonds to identify when oxidation and reduction are occurring, right? So for oxidation, we'll use the symbol of O in the square brackets, and for reduction, we will use hydrogen in the square brackets. All right, so the emphasis here, oxidation is a gain in bonds to oxygen, right? And this is bonds of carbon to oxygen, or the loss of bonds between carbon and hydrogen, all right? So let's look at an example. Let's just look at a simple alcohol right here, right? So here is the carbon that's bonded to the oxygen. So notice that there's only one carbon to oxygen bond. And now, if it undergoes an oxidation, we can go to the aldehyde, right? So here is the carbon that's still bonded. But now notice there are 2 carbon to oxygen bonds. So notice that there's the same number of oxygen atoms, but we have more bonds between the carbon and the oxygen. So that's why this is an oxidation. For reduction, we look at the number of carbon-hydrogen bonds. So in this next example, there won't even be any oxygen present. So we'll go here, all right? So we could take 2-butene and make butane, and this would be a reduction because we have a gain in the number of carbon-hydrogen bonds, right? Or we'll do some more examples and we'll see we have a loss of carbon-oxygen bonds. So you want to think of oxygen and hydrogen as opposites here, the redox complements. To help us see this a little more clearly, where we have the change, it can be a very good idea to write in the hydrogens, right? Because oxidation and reduction of organic compounds could involve changes in the number of hydrogen atoms, and typically in a skeletal line structure, we don't show those. So here, would be showing the missing hydrogens where we have the change, and then notice in the reaction, now we are gaining 2 carbon hydrogens, right? So we have 2 new carbon to hydrogen bonds. So since we had a gain, that's why it's a reduction. Now I do want to point out one thing here. We recently studied acid-base chemistry, right? So H plus is a hydrogen ion, and that's acid-base chemistry. The H in the square brackets, that represents hydride, and that's redox chemistry. So hydrogen is very tricky, right? It's the only element that we're studying that can be positive or negative, and that's when it's positive, it's taking the role of a proton for acid-base chemistry, and when it's negative, it'll be a reducing substance, hydride. All right, so let's practice applying this knowledge. Let's build our wisdom. So here are 3 practice reactions. So this would be a great place to pause the video and try to answer them on your own and then compare answers. Okay, great. Let's see how you did. All right, so on this first one, we see where the change is occurring. So let's draw in the missing hydrogens so we can look for change. And then we can see this is actually the reverse of our practice, right? Here, we lost carbon to hydrogen bonds. And so that would be an oxidation, right? So here's the reduction and the oxidation. They can go back and forth. Here we are looking at the change. So we notice change here and here. And so we notice that here we just have 1 carbon, oxygen, and 1, and now we've doubled, right? So we've increased the number of carbon to oxygen bonds. So this would also be an oxidation. And then this last one here, we look for where the change is. Anytime you see the change, it's a good idea to write in, right? So those are the original hydrogens. And then we notice that now we have 2 more. So we gained carbon to hydrogen bonds. So this would be an example of a reduction. Alrighty. Okay, so let's build on this a little bit and practice. So here, this one is a little more advanced now. This question is letting you know the process that's occurring, and we need to predict the products. And then let's practice our functional group classifications because we need to reconnect with those organic functional groups. All right, so here we have an aldehyde, right? And here's our carbon to oxygen. So if we are going to do an oxidation, right, we have to increase the number of carbon to oxygen bonds. So the aldehyde will oxidize to the carboxylic acid, right? Or we could undergo reduction, right, and take away one of these carbon-oxygen bonds. And so then we would simply have an alcohol. Right? So here we added a new carbon-oxygen bond, and then here we took it away. And so now this would be a primary alcohol. Okay. So aldehydes are one of the trickier groups because they can be oxidized or reduced. Here we have a secondary alcohol, and it helps to focus our attention where the carbon-oxygen bonds are occurring or where we see double bonds where change could take place. We want to oxidize, so we want to increase the number of carbon-oxygen bonds. Well, here we have less options, right? This carbon is already pretty committed, right? It's got a bond to a carbon on the left and a bond to a carbon on the right. And so all we can do is put a double bond there, and there's no more options. Carbon's limited to 4 bonds. We're done. And I'm sure that you recognize this as a ketone. All right? So we will have a follow-up video that will really emphasize and go through the oxidation of alcohols and the reduction of these carbonyl compounds. They're very important to our study of biochemistry that we're working towards. Here's an example now that brings together what we've learned about inorganic oxidation and reduction and organic oxidation and reduction. And this is the test that's done on breathalyzers. So while I have no personal experience with this, I do have some friends that bought some of the breathalyzers for a party, just kind of for fun. And when we blow into them, the breathalyzer starts red. This compound is red. And then, if there's alcohol in our breath, as we blow the alcohol into the red compound, a redox reaction occurs, and the chromium compound will change. I don't want to give away the answer. And then it becomes green. And so the more green the breathalyzer tube becomes, the more alcohol is in the person's breath. So there's a real life example. Now let's apply our chemical understanding. Alrighty. So if we look here, we look at this carbon, and it has 1 carbon to oxygen bond, and now it has 3, right? So using our organic rules, this is definitely the oxidation. All right. Now, so we know that we can pretty much already know that this is going to be the reduction, but let's convince ourselves of that. All right, so let's practice what we've learned, right? The hydrogens are always +1. The chromium, we don't know, question mark. And then our buddy oxygen will always be oxide. Okay, so remember, right, now we make our algebraic expression. So the chemical formula tells us there's 2 hydrogens, and they're each +1. Here, right, the chemical formula tells us there's 2 chromiums, and we're not sure what the charge is. And then there are 7 oxides, and they're each -2. And when we add this all together, it should be 0. So algebraically, right, we end up with 2. And then this would be, I'll just make that into an x, and -14, right? And then we do the algebra, and we find out that x is +6. So chromium is +6. Oops, sorry, I forgot to slide my page, right? But you guys are good at algebra, so that's good. Now let's look over here, right? There's 2 chromiums, and we don't know their charge. And then we're going to add that. Right, and then there's the 3 oxides, each -2, and it's a neutral compound, adds to 0. So when we solve for x here, it's going to be +3. So chromium +3, oops, +3. Let me write that together, make it pretty. There we go. All right, so we can see, looking here, right, we did our half reaction, right? Chromium would need to gain 3 electrons. chromium 6 would need to gain 3 electrons to become chromium plus 3, and gaining electrons is reduction. So there's an example of how organic and inorganic oxidation and reduction can come together. Alrighty, so we have one last page to go over. There's one more important concept about oxidation and reduction that we need to learn. And this is about the idea of oxidizing agents and reducing agents. All right, so at first it feels a little clunky, but we'll get used to it, right? So it's an oxidizing agent. So that means the reactant gets reduced, right? It helps, it's an agent. It helps other compounds oxidize. And so the way it does that, how does it do that, right? By being reduced, right? So an oxidized compound wants to lose electrons. So somebody has to be able to gain them. There has to be an electron handout somewhere. So that's where this idea comes from. Okay? And then reducing agents will be the reverse. This is the reactant that gets oxidized, right? It helps other compounds reduce, right? And so it's just the reverse. And how does it do that, right? By being oxidized, right? So being the partner in the electron handoff, right? So reducing is gaining electrons. So if a compound needs to gain electrons, it has to get them from somewhere. So the reducing agent loses its electrons so that they can be gained by another substance. So it's a partnership. Alrighty. So let's put this together with one last practice problem. If you're feeling confident, go ahead and pause the video and see how you do. And then compare answers. Otherwise, we'll work together. All right? So remember, just from the very beginning of this video, step 1 is we need to determine the oxidation states of every element. Zinc, it's easy. It's pure. Hydrogen, +1. Halogens, -1. Wow, this has been really easy so far. Zinc, +2. So now we have a change. And, excuse me, here's hydrogen, right? It's pure. That's 0. And then our buddy chloride also remained unchanged. So we have another change here between the hydrogen. All right? So we have identified our 2 elements with the change of oxidation states. Now I'm not giving you so much guidance here. Now we have to find the oxidation, right? So oxidation is loss of electrons. So who lost electrons? The zinc, right? The zinc is the Leo. And the hydrogen had to gain electrons. So this is our GR, our reduction. All right? So the zinc started at 0, oxidized to zinc +2, and there's our lost electrons. Well, the hydrogen, right, it started as a +1, and then it goes to hydrogen that's pure. Have no fear of ice-cold beer. So here we are going to need to put coefficients in our half reactions. And so the hydrogen gains 2 electrons. So it's nice and neat. Electrons lost. And there's electrons gained. Okay, now, so now here we go, reactant, right? So when we get to oxidizing agents and reducing agents, we're talking about the full compound, the reactant. So which reactant is the oxidizing agent? That would be the hydrochloric acid. And which reactant is the reducing agent? That would be the zinc metal. Alrighty, so oxidation and reduction are big topics, And this would be a great time for you to go and work some of your post-video practice problems to reinforce your understanding.